Hi everyone, welcome to today's lesson. Well, today we're going to be talking about things falling through the air. So let's say, for instance, you look at the picture that's on the screen right here and you notice that there is obviously a car falling out of the plane, which seems kind of strange and everything like that, right? The question is, what happens is the plane, pulls away and the car falls down, right? Does the car get going faster and faster and faster? Well, sure it does and everything, right? It's got to, right? As gravity pulls down on it, which is going to be the answer for the question of the day today, is going to be this guy on here. There we go, is gravity. Why is it that objects accelerate as they fall down faster and faster and faster? Yeah, gravity is the thing that's pulling it down. So that's what the main lesson is for today, is things falling down. So if you have a situation where the only thing that's working, the only thing that's pulling on the object, let's say that car as it jumps out of the plane, right, that's pulling it down faster and faster and faster is gravity, that's where you have something called free fall. Now here on Earth, it's very hard to get free fall because we've got all this pesky air in the way, right? That air that's flying all around all the time. That slows things down and everything, right? If you remember in class, I showed you the example where if you have two pieces of paper, right, that are exactly the same except one's all crumpled up, which one falls faster? Well, certainly the one that's all crumpled up falls faster because the air doesn't get in the way, right? So here on Earth, it's very hard to have free fall. But if you also remember the example that we did in class of on the moon back in the 1970s, they did the same experiment where they had a feather on one side, a hammer on the other side, and they dropped them. And when they dropped those two objects, they were said to be in free fall, right? Because the feather and the hammer, they both fell at the exact same rate, right? Or if you also remember, there was another video that I showed you about they were inside a chamber where they pumped all the air out, and they had, I think it was like a bowling ball and some feathers. And same thing, in free fall, they both fell in extreme slow motion at exactly the same speed, right, for it. Normally here on Earth, if you did that experiment, right, the bowling ball would drop really fast, the feathers would kind of like, because they got to push their way through the air as they go down. So free fall is very hard to achieve here on Earth because of that, all right? Now, the thing that's doing it is this thing called air resistance, right? It's the friction of those little air molecules as they're bumping, as things are bumping into them and everything. And this is where we get into the aerodynamics, let's say, of a car, right? I've got a picture of a car right here. And you can see modern cars that are meant to go really fast, what you want to do is you want to make it as aerodynamic as possible so the air can easily flow over that object very smoothly for it. Right, so that's what's going on with air resistance. So a car driving down the road would be a great example of this. The air's flowing around it, right? It's trying to minimize the air resistance as much as possible. If you have a parked car, well, that'd be a good non-example, right? It's not doing anything at all with that, right? So that's what's going on here with this. Let me see if I can get this to work. Here you go. So here's an example. This is when, Ford, I think this was a Mustang, was being tested. This is actually before they made it available to the public, right? What they do is they test the aerodynamics of the car. They have a little stick right here that's shooting out high pressure air. It's got a little bit of some kind of foggy smoke stuff in it so you can see where the air goes. And you can see the air travels around the car. And interestingly, when it gets to the top here, it doesn't just kind of fly off in a straight line or keep going up. It actually clings back to the back of the car. It actually follows the shape of the car. So that's why it's very important. Not only the front of the car is aerodynamic, but the back of the car, they have to think a lot about the shape of the back of the car for the wind to keep going and everything to make the car very efficient. So it, the more aerodynamic the car is, the easier it is for it to slip through the air, and that means that it's going to have better gas mileage, compared to a car that doesn't have that flowing smooth motion. So here's a concept car right here where, they show you all those wind, air molecules moving around it, how they move around the car very, very efficiently. Right, here's a prototype design. This was actually from several years ago. This man right here designed it, and this would be like the new version of a semi-truck, right? So the back end of the truck ends up kind of being the same as it is today as far as it's a big boxy square kind of thing, a rectangle going down the road. But the front of the trucks, right, the cab of the trucks, you can see is dramatically different, right? And I forget the numbers, but it was a huge amount of money that would be saved on a truck every year in gas money because it would be so efficient. The air would just flow around it and over it so efficiently and everything, right? So that was one design that they had for a new truck. Here is my beloved Jeep. I had a Jeep a while ago, and while I loved it desperately, it was not very fuel efficient as far as the aerodynamics go, right? So when you're doing these wind tests, right, just like when we saw that the wind blowing over the Mustang, right, you're looking for it to be a nice smooth flow, right? Anytime you see air eddying, kind of like in little circles here or over here or behind it, right, that's inefficiency. That's places where the air molecules are bumping into it unnecessarily, and it ends up using more and more gas, right? So that, as far as aerodynamics are concerned, this would be an example of what you don't want. This is something not very efficient aerodynamically. Now, most modern cars have gotten very good at aerodynamics. Two places where modern car designers are kind of turning their attention to nowadays is, well, first is just underneath the car, right? The top of the car might be all smooth and the sides are smooth and everything like that. But what's going on underneath of the car, the air that goes under the car, well, that matters too. So modern cars, often they try to make the bottom of the car as flat as they can, right? Now you're still going to have different, things going on that are going to be unaerodynamic, and it's almost inedible underneath the car. But they're trying to do it as much as they can. Try to think, how can we get air to flow smoothly underneath of the car so that it makes it more efficient? And to the extreme level, some designers are even talking about, okay, the air that goes into the front of the car to cool the engine, what happens with that? In most cars, even modern cars, the idea is the air comes in, it hits the radiator to help cool off the engine. But after that, who really cares? The air goes all over the place and eventually gets out somehow, right? But some designers are thinking, what if you could have a way where the air flows in through the front of the car, it cools the radiator, but then there's kind of like an escape port somewhere in the car where that air can easily flow and get out. That would make the car much more efficient. It would be more aerodynamic on the outside and on the inside of the car. Okay, it's time for another traumatic story from Mr. Jackson's past right here. This true story happened when I was little, right? My sister and I would go visit my cousins that lived in New York City, right? And my cousins would taunt us all the time about us being, hillbillies, hicks, and everything like that, much to our horror, right? So when we go into part of the city where there were the big skyscrapers and everything like that, they would tell us this story right here, because they noticed, like my sister and I, we'd be looking up like, whoa, look how tall the city, the big buildings are and everything like that. So they kind of like tell us this story. You don't want to look up because people that are, way up high, let's say on the Empire State Building and everything like that, they get to those observation towers and they take pennies. Where's my penny? Here's my penny. They take pennies and they would chuck them off the top of the skyscraper. And because of free fall, right, the pennies would get going faster and faster and faster and faster, right? They get going eventually so fast by the time they made it all the way down the street level that if you happen to be like there just standing in the wrong place at the wrong time, the penny would smack you in the head and just embed it, wait for the special effects, and embed itself about halfway into your head is what they would tell us and everything. And you die, that was what they tell us. So for a while, we believed that, and we were very terrified to walk around in New York City as little kids because of this and everything. So my question is to you, is this a true story? If you take the average penny and you toss it off the top of a building, right, in New York City, and it falls down, 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 down from one of the really tall buildings, not, I'm not talking like 10 stories high here, right? Would it hit you and kill you and everything? Well, if you do this and everything, think about it, right? If that was the case and people were dying all the time in New York City and other big cities around the world because of penny strikes, you'd almost hear about it on the news. Just like, today, I don't recommend you go to New York City right now, but, maybe in a few months or a year from now, maybe it'll be safe to go there again and everything. But you don't hear about people being hauled away in ambulances in New York City because of penny strikes, right? Today, we hear about it because of the virus and everything, which is why we're here at home. So it doesn't do it because of what, right? If you're here, here's a picture from, this is a picture literally from the top of the Empire State Building at the observation deck. And clearly, if you've ever been there, there are just these kind of like grate-like things right here. You can easily stick your hand through that, right? It's designed so no one accidentally falls off or anything like that. But it's certainly not protecting, the average penny from being thrown out of the observation deck. Here's another picture from it and everything, right? So why is it that the penny, if it's falling faster and faster and faster, it doesn't eventually stop? Well, it comes to our last vocabulary word of the day, terminal velocity. Right now, terminal velocity, right? This is basically the greatest velocity that a falling object can achieve just by gravity alone. So if you take a penny and you were to chuck it off the Empire State Building, right? I mean, the only thing that's going to make it move down, right, is going to be gravity, because you got to throw it out to get past, the actual, through the observation deck and everything like that. Gravity is the thing that's pushing it down, down, down. And sure, for the first couple floors, gravity is pushing it faster and faster and faster, right? This brings us all the way back to the question of the day, right? That car fell out of the plane, hopefully not by accident, but maybe, right? And sure, as it keeps falling, it gets going faster and faster and faster and faster, right? But eventually it evens out, just like the penny, right? Eventually, gravity's pushing down with the same amount of force all the time, but eventually, the faster the penny gets going, those air molecules are pushing up on it, right? And eventually the two balance out, right? The air molecules are pushing up with a certain number of force, gravity is pushing down with its certain number of force, and it balances out. And when that happens, when the penny is falling, 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 and it reaches that time where it's not falling any faster, gravity can't push on it any harder, the air molecules aren't slowing it down anymore because they can't push on it any harder, that's where you get to terminal velocity right there. That's where the penny is thrown off the building, right, for us, right? So the net result is as the penny falls down, 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 even if it did fall all the way down to the street level and everything, if it hits you in the head, it's going to be more like, ow, that hurt, but that's about it. Then you move on. Think about it. Another way to do this is if the pennies really were moving unbelievably fast when they hit the ground, you'd see them kind of embedded down into the pavement everywhere. You'd go anywhere in the city where there were big, tall buildings, look down, and there'd be little penny, at least dents into the pavement and everything like that. So the good news is you don't have to worry about it. It's just kind of it's kind of like an urban legend that my cousins told me as a little kid. We were kind of gullible and everything. Now, normally in class, I'd have you do this worksheet right here in your workbooks, but you don't have to worry about that. Instead, all we're going to do is we'll just go over the answers that we would do in class anyway and everything. So one of the questions is this guy right here. When an object is said to be in free fall, right, it's only when that object is being pulled down just by gravity, right? Gravity is the only thing that's forcing the object down for it. There's no other forces involved in this, right? So the easy example for this would be on the moon, right, where there's no air to get in the way. Right, so it's just, it's just falling down, gravity's pulling on it, nothing else is in the way, no air or anything like that. It's not that you can't do free fall here on Earth. Remember the video again of the bowling balls and the feather, but it's just very, very difficult. You got to get rid of all the air. Question number 2, objects falling through the air experience a type of fluid friction called air resistance, right? Because of that air resistance, that's what slows things down and everything. That's where when the space shuttle used to come back down into Earth's atmosphere, right? It hits a humongous amount of air resistance, right? Normally it's traveling above the atmosphere, but as soon as they slow, they fire jets the opposite way it's going, so it slows it down, it starts falling, right? And then it hits a tremendous amount of air resistance, and that slows it down even more, right? Question number 3, right? The greatest velocity a falling object reaches is called, do you remember? Terminal velocity, right? So terminal velocity, right? Gravity is pulling down with a certain amount of force, air is pushing up with a certain amount of force, and that's as fast as you go. So let's say you're skydiving, kind of like the person in this picture right here, right? When they jump out of the plane, sure, they get going faster and faster and faster for a little bit, but after a couple seconds, it doesn't take very long, you reach that terminal velocity and you just fall for the next, amount of time, depending on how high you are, at the same speed the whole way down. True or false? The greater the surface area of the object, the greater the air resistance. That's definitely going to be true. That's how parachutes work. They have a humongous amount of surface area. And so what that does is, that slows you down because you have more air molecules hitting the whole thing for it over and over and over again. Right? Which object is going to hit the ground first, right? An object dropped or an identical object thrown horizontally. Right? So again, this is an example that normally I'd show you in class, but I don't have the little machine that does it. And all they do is they have 2 ball bearings, right? They're kind of beside each other right here. One of them gets shot out, right? The other one gets dropped at the exact same instant, right? And so what this does is it kind of shows you, right? Even though one's being shot out this way, right? It's falling at the same speed as the one that's just dropped straight down. So this, when they get here, they're both at the same height, right? When they get down here, they're both at the same height. Down here, they're both at the same height. And this is a common physics example that happens, right? They ask the question, let's say you have a cannon that shoots out a cannonball this way, and you have a cannonball that just drops, right? Well, what happens is, even though the cannon shoots the cannonball out this way, it's still, as fast as it's going this way, it's still going down too, just like the one that you dropped, right? So, the cannonball that gets shot out, it's dropping at the same pace as if you just stood there beside it and dropped the cannonball down, straight down towards your feet and everything, right? So they're going to be exactly the same for number 6, right? An object that's thrown is called, do you remember this? We did this one in class, projectile, right? So a projectile, doesn't matter what the object actually is, whether it's an apple, cannonball, or a pencil, right? If you throw it, it becomes a projectile while it's being thrown, right? Falling objects have more air resistance, right? When there's a larger surface area, right? So the larger the surface area, the more air resistance you have. That's where we get to my wingsuit person right here, right? If you've ever seen one of these wingsuits, they're designed to increase surface area. And that surface area means you have more air resistance, right? In some cases, you want more air resistance, kind of like this guy right here. Yeah, this person is flying along through mountains and everything for it. And there's some direction. They have some direction because look at all this extra surface area that they have on their wingsuit, right? Because of that, they can literally kind of bend it one way or the other, and they can direct which way they're falling. And then the net result is they can actually control which way they're going. And then there are lots of videos, if you kind of YouTube this, where the wingsuits, you can get, in my opinion, dangerously, concerningly close to the mountains as they're falling, as this person's doing right here. I don't recommend that anyone tries this. I don't know that your mom would like this. It's not looking very safe and everything. So in this case, they're using the air resistance to their advantage to have a little bit of fun with physics right here. Okay, number 8, right near the surface of Earth, the acceleration due to gravity is 9.8 meters per second per second. After falling for 6 seconds, an object would have a velocity of, well, all you got to do is just multiply again, right? Multiply that 9.8 times 6, and that's going to give you the answer of, hold on here, 58.8 meters per second, right, is going to be your answer that you would have for that. Number 9, air resistance is a type of fluid friction, right? So we're moving into fluid friction here, is where we're going to be moving into next week for us. We'll be talking about some fluid things and everything. Question number 10, following objects stop accelerating and reach a terminal velocity because of, well, if you remember, air resistance, right? That air is the thing that's getting us in the way, right? So remember, gravity is pushing down, right? Air resistance is pushing up. That's where you have that terminal velocity. When the two of those are balancing each other out, that's what's going to cause that, that amount of air resistance to be equal. Normally I'd show you another video, but I'm going to conclude that in a link for you. So you're going to, after you're done watching this main part of the lesson, there's a short little link. It's all about someone basically surviving when the plane crashes and doesn't land normally and everything like that with the Mythbusters. It's pretty short. Then there's a short reading attached to this. You don't have to worry about the page numbers. I just have it right there linked in for you to read. After you're finished watching this, watch that short video, do the reading. You don't have to highlight or anything like that. Then the last thing for today is just complete the short quiz for today. And then, believe it or not, I think this actually concludes the chapter that we were in for us. And next week, we're going to start the next chapter, right? So.